Hi, this is Professor H. Rahman from Agricultural and Food Engineering Department. I welcome you all to this NPTEL course on traction engineering. Today, I'll try to discuss how to measure the contact area of a pneumatic tire. As I said, contact area, first I will try to identify what are the different parameters which are going to affect the contact area and the tire deflection. So if I try to find out the parameters which are affecting contact area, it will be the load which is coming on the wheel. It depends on the type of tire, it depends on the inflation pressure, it depends on the soil condition. So in our experiment, we are going to find out contact area on a hard surface, and we will take a bias ply tire at a maximum load of 1000 kg, and what I will do is I will vary the inflation pressure, and corresponding to that inflation pressure I will try to measure what is the tire deflection and what will be the contact area by taking the footprint of the tire. So as I said, bias ply, radial ply. Obviously, radial ply will give you more tire deflection as compared to bias ply. So that is known. So only my aim is to find out how to measure the contact area. So that's why whether it is a radial tire, bias ply tire, doesn't matter. The procedure remains same. So that's why I have restricted my study to only one kind of tire at one inflation, at one load and at one soil condition. Here the soil condition is hard soil. Today I am going to explain how to measure the contact area of a tire. Contact area of a tire is important from the point of view that tractive effort is developed by a tire. So it is the contact area which is directly controlling how much force or the tractive force will be developed. So contact area is a function of different other parameters like what is the inflation pressure, what is the strength of soil, what is the load which you are applying, and what is the type of tire. So in today's class what I will do is I will restrict this study to a particular tire. Particular tire means I have taken a 13.628 bias ply tire, and I will try to measure the contact area on a hard surface. So we try to apply a load and then we vary the pressure. So since I told in the beginning that contact area is a function of load, is a function of type of tire, it is a function of inflation pressure, is a function of soil condition. Now you have fixed the soil condition. Here the soil condition will be on a hard surface. That means the soil condition is hard. Now the other variables I will try to restrict the load to the maximum load carrying ability of the tire, that is 1400 kg, and then what I will do is I will try to vary the inflation pressure. So I will get different contact areas. So I will measure those contact areas by following a certain procedure. In addition to that, we will also measure the deflection of tire, because when you are going to calculate the tractive effort developed by a tire, there we are utilizing Brix's equation where we require the deflection. So when deflection is more, obviously the contact area will be more. So deflection will be more means either we, for a given soil condition, if we increase the load and keeping the inflation pressure constant, then deflection will increase. In other words, if we keep the load fixed, vary the inflation pressure, contact area will be changed. That means is the tire deflection, which is a function of load as well as the inflation pressure for a given soil condition. So now I will show you the procedure which I will follow to find out or to measure the contact area. As I said that the contact area will be measured on a hard surface. So I have put this blue plate, this is a MS plate, over which I will try to take the contact area. So what I will do is I will put a uh, seat, white seat. This white seat is very interesting in the sense I have to take the footprint. So I have taken a carbon seat in between. That means the lower seat, the footprint will come, and to protect this carbon seat from damage, we have to put a white sheet on the top. So this is a sandwich of two drawing sheets with a carbon seat. This has to be put below the contact, below the tire footprint. So what I will do is I have to raise the tire. So you can see here there is a gap between a plate and the tire lower surface. So that gap will help us to put this seat where I will take the footprint of the tire. So I'll now try to put this seat, then I'll slowly release the tire so that it will rest on this seat. Then I'll repeat that exercise by rotating the wheel 2 to 3 times so that I can get a clear print of the tire footprint. Now I have put the drawing seat below the tire, and the seat has to be clamped because good amount of weight is coming on the seat. That's why it will be disturbed. To prevent the seat from disturbance, we have clamped this seat which is put on the MS plate on both the sides. Then I'll slowly put the tire over the seat. This raising and lowering of wheel is done by a hydraulic arrangement, so everything will be done very smoothly. Now on both the sides we have clamped, so the paper is almost flat, there is no crease in between. So next procedure will be I will try to lower this plate, this wheel over the seat. Now when I lower the tire, I should see that the tire doesn't rest over that seat, because that will give you some error results. So what I will do is I will try to see whether the tire is just touching or resting. To verify that one, I have put a sheet of paper. You can see the person can easily remove that paper. That means the tire has just touched the seat. The entire load is not transferred onto the seat. When the tire is just touching the drawing seat which I put below the tire, I should know that that is the zero condition. So what I have done is I have measured the depth of that one with respect to the rail which is provided here. Over this rail, and one end of this rail is supported, this depth gauge is there, the other end is fixed. So now if the tire is going down, when it is transmitting the load onto that drawing seat, then there is a deflection. So I'll initially take the zero condition, and then finally whatever reading comes, that difference will give you what is the tire deflection. Now I'll lower the tire to touch or to transmit the entire load onto the drawing seat. Now the tire is almost resting on the drawing seat. That means the entire weight is transferred. So I will get a footprint. To make that more clear, what I will do is again I will raise that tire, rotate it, then do the same exercise. That means I will again lower it. So this way I will continue for 3 times so that there will be a clear-cut print of the tire footprint will come on the drawing sheet. Initially the reading was, that means when it was just touching the drawing sheet, the reading was 24 centimeter. Now the final reading is coming as 32 centimeter. That means the tire has deflected by 8 centimeter. This test was carried out at a pressure of 14 psi and a load of 1400 kg for a 13.6 bias ply tire. Now the tire is rotated to a different position, so the another surface will come in contact with the drawing sheet. Now we have removed the clamp, and then I will remove the upper seat, that is upper drawing seat and the carbon seat which is present. Now we have removed the upper two seats, that is drawing seat and the carbon seat, and the lower seat where the footprint has been taken, we can see very clearly some print has come on that seat. Now I will remove that seat and will show you how what is the shape of that footprint which you obtained. Now the footprint which I got, I have removed that seat. You can see very clearly the shape, the very good shape which I have got. I will show you what will be the length of that contact area. So this is 48 centimeter, 49 centimeter is the length of that contact area, and width will be 31 centimeter. This is not a square, this is nearly parabolic type of thing. So 31 centimeter is the width and 48.5 centimeter is the length. I have drawn the outline of that footprint area, and I have measured the length and width. So similar exercise I will carry out for different other pressures. As I said, deflection has to be varied, so I will try with a different inflation pressure. And the footprint which you got is this one. This is at a pressure of 10 psi, inflation pressure, load remaining same. In this I have also reduced the load so that we will get more deflection. That means we will get lesser deflection. Because we have reduced the load, inflation pressure we have decreased, so you will get another set of data. Then we increase the inflation pressure. It was 10 psi, now we have increased to 18 psi, so you will get, this is the footprint of the tire. This is at 12 psi, 1000 kg. This is the shape of the tire, footprint of the tire. So likewise, we have carried out different exercises for different pressures and load combinations to get a set of data, and then from there we will try to find out how contact area is changing with load and changing with inflation pressure. The tire deflection which you measured, that is converted into deflection percentage. How I converted it? Whatever deflection I got, that I have to divide it by the section height minus the flange height into 100. So that means in the numerator is the parameter which you measured, that is tire deflection, and the denominator is the difference between the section height of the tire and the flange height. The section height of the tire is calculated from the tire specification. The tire specification which we use is 13.628 tire. So the section height is aspect ratio into section width. So 13.6 is the section width and aspect ratio is 0.75. So we can multiply and find out what will be the section height. So in the denominator we have section height and flange height, that is the difference. So numerator and denominator, then we multiply the ratio with 100 to find out deflection percent. So what I have done is, for different inflation pressures starting from 10 to 22 psi, what is the deflection percentage which you obtain, that I have plotted. So clearly it indicates that with increase in pressure, the deflection percentage is reduced. Is obvious, because when you are increasing inflation pressure, that means you are putting more air into the tire. So it is the air which is supporting the load. That means load is not transmitted to the tire carcass. So that's why deflection is reduced. So more the pressure, more is the air into the tire, and air will carry the sufficient amount of load which you are putting, and it will not allow the load to transfer it to the tire carcass. So that's why deflection is reduced. Now coming to the contact area, the footprint which you obtain that were transferred to a solid works, and from the solid works we could able to calculate the contact area. The other method, simplest method is put it on a graph sheet and then use a planimeter, then you can find out contact area. So we have done the first part, that we have transferred the image into SolidWorks. Then from the SolidWorks we calculated what is the contact area. Now that contact area is again plotted against inflation pressure starting from 10 psi to 22 psi. So what we observed is a trend which is similar to the tire deflection. That means with increase in inflation pressure, the contact area is reduced. It's obvious, since deflection is less, so contact area will be less. That means is the air which is resisting the load which should come onto the platform where we try to measure the contact area. It is not allowing that load to come onto that drawing sheet or the platform. Now, since load is not transmitted to the tire carcass, so obviously there will be lesser deflection and there will be lesser contact area. So contact area is important. That's why I have demonstrated this procedure how to measure contact area, and that we have taken on a hard surface. You can carry out similar exercise on a soft surface, but in the soft surface the contact area will be varying from what we observe on hard surface, because the resistance which is coming from the soil will not be there. In case of hard soil, whatever resistance you are getting, you will not get that resistance in soft soil. So obviously the contact area will change. So in our study, since we have limited our study to a particular condition, that is the hard soil surface, then we have limited the study to a particular load, which is the maximum load carrying ability of a tire, and then what we varied is, and we have also limited the tire to a bias ply tire. So my aim was to just to show how to measure the contact area so that you can have some idea. And since contact area is the important parameter which is deciding the maximum tractive effort or the tractive effort which is developed at different slip values, so that's why my aim was to show you how to calculate the contact area. So I have demonstrated this one. I hope you have understood how to measure the contact area, and you can utilize these values for calculating the tractive effort. Thank you.